Hey everyone, welcome to Math 106. We're working on section 4.2 today, special applications of ratio and proportion. So maps and blueprints are scale drawings, which means they're in the same proportion as the actual object. And that means that the ratio of length to width of the scale drawing has to be the same as the ratio of the length to width of the actual object. And we can use this to solve problems. So for example, we have a city park that's 150 meters long and 100 meters wide. And the map of the park displayed in an entrance is 1.5 meters long. How wide is the map? And then we're going to find what's known as the scale factor for the map. And that's the ratio of the size of the object in the drawing. So we're going to set up a proportion. And I'm going to start with the city park's dimensions. Now since all the units are meters, we should put a little bit more information there so we can differentiate between the length and the width. So 150 meters long, 100 meters wide. Now the drawing is 1.5 meters long. Since we're talking about the length of the drawing, this has to go on top because in the original rate, I put long on top. So length on top in both of the fractions, width on the bottom in both fractions. We have to be consistent when we set these up. We don't know the width, we're going to solve for it. So I'm going to declare a variable w for the width of the drawing. And now we have the proportion set up, we can cross multiply and solve. So cross multiplying, denominator by numerator, that's 150w equals 100 times 1.5. Multiplying over here, we get 150w equals 150. Divide by 150 on each side, and w equals 1. And the answer should have three parts: the number, the units, and what we're talking about. The sign is 1 meter wide. Your turn, number one. A CAD drawing of a machine part is 6 inches wide and 8 inches long. The part is 20 inches long. How wide is the part, and what is the scale factor? Oh, I forgot the scale factor. Hang on. Okay, scale factor is the ratio of the size of the actual object to the size of the drawing. Now I could use these values, but I calculated this one, and if I made a mistake here, that's going to carry over into the scale calculation. So I'm going to use the given values. So the ratio of the size of the actual object to the size of the drawing is 150 to 1.5. And if we reduce this, so we have a denominator 1, you can do it like that. The scale factor is 100 to 1. Right? The actual area is 100 times bigger than the map. Right, back to your turn, number one. We're going to do the CAD drawing of a machine part. So the drawing has dimensions 6 inches wide and 8 inches long. It doesn't matter which one we put on top as long as we're consistent. The actual part is 20 inches long. So there's our proportion. Notice we have length on the bottom, width on the top in both fractions. Cross multiply. 8w equals 6 times 20, so 8w equals 120 divided by 8, and we get w equals 15. So the part is 15 inches wide. Now let's do the scale factor. So with the given information, we know we have 20 inches of length of the actual part, 8 inches length of the drawing. So the ratio is 20 to 8. If we reduce this fraction to the lowest terms, divide the top and bottom by 4, we get 5 halves. So we're going to write in colon notation. See, the scale factor is 5 to 2. Now we're going to discuss a concept from geometry. It's called similar figures. And similar figures are proportional, which means these three sides are in proportion with each other exactly the same way as these three sides are in proportion, or these three dimensions. So length, width, and height. Length, width, and height. So basically, one figure is just the other one blown up. It's exactly the same figure, just larger. And those are similar figures. And since they're proportional, we can use proportions to solve any problems using similar figures. So here's some triangles. Now these are going to be similar figures because they have the same angles. And you notice that certain angles have the same markings in them. That means those angles have the same measure. So that means this angle here, which we indicate by a capital letter for the angles. So this is angle F, and this is angle C. They both have two markings, so those two angles are equal. And same with A and D. This angle is equal to this angle. And in a triangle, if two angles are equal, then the third must also be equal. So that means angle E is the same as angle B. Now we denote the side lengths by the same letters as the opposite angle. So if this is angle B, you go through the triangle to the other side, and this is also side length B, except for we use small letters to indicate the side length. Capital letters for the angle. So angle E, side length E on the other side. Now if we want to set up a proportion for similar triangles, we have to locate the corresponding sides. And the corresponding sides then can go into the proportion. So for this one, we want to find the side lengths that are proportional. And those are the side lengths that are opposite the equal angles. So we have angle B equal to angle D. The opposite sides are B and E, so B and E are proportional. So the corresponding angles are B and E, A and D, C and F. And then the corresponding sides are the same letters, but the small letters. So B corresponds with E, side A corresponds with D, side C corresponds with F. Your turn number 2. Here's a couple of similar triangles. Now these were in the same orientation, so we could very easily pick out the corresponding angles and sides. But these are in a different orientation, so you have to go by the markings. Right, just a reminder, during the your turns, I'm not going to pause. I'm not going to stop to give you time to work, so pause the video, and then when you're done, come on back. All right, corresponding sides here, we notice these have the same markings, so R and N correspond. And then No markings here or here, so S and P correspond. And then those with two markings, T and M. And now for sides, opposite side M, got an M here, got a P here, and an N here, T, S, and R. So corresponding sides, R corresponds with N, S corresponds with P, and T corresponds with M. And it's those corresponding sides that we use in the proportion. So here's an example of solving an equation or solving a problem involving similar triangles. So we're referring to figure 3. If A is 8, so A is 8, B is 12. We have those two side lengths. D is 6, we got one down here. Notice that we have some corresponding sides here, that's what we want. And then we have E as the unknown. So we're going to find the length of E using a proportion. So setting up proportion, there's a bunch of different ways we can do this. I'm just going to start with a big triangle and do this side over this side. 8 over 12. That's side A over side B. Now, what corresponds with side A is side D. So in the other equation, pick the corresponding side and put it on the same side of the divisor line. And corresponding with B is E. So E goes down here. And now we can fill in the numbers. All right, A is 8. So we have 8 over B is 12 equals D is 6 over E. Now we have a proportion, we can solve for E. So E times 8, so that's 8E equals 12 times 6. E is 72, divide by 8, oops. Divide by 8, and we get E equals 9. Now if we want to check, what we can do is divide 8 by 6, get a decimal, and then divide 12 by 9, get a decimal, those decimals should match. And in this case, they do. All right, your turn, number 4. Your turn, number 3. So we're referring to figure 4. If n equals 12, r equals 16, t equals 24, find the length of side M. Right, there's a couple of corresponding sides, r and n. And then we got t equals 24. And we're finding the side length M. So T and M correspond. All right, so I'm going to create a proportion here. Let's do T over R equals, so one triangle, we go over the other triangle, and the corresponds with T is M, so M goes on top, and N corresponds with R, so N goes on the bottom. That's one way to set it up. Bunch of different ways you can set these up as long as you're consistent. All right, let's plug in the values. 24 over 16 equals M over 12. All right, cross multiply to solve. So 16M equals 24 times 12. That gives us 16M equals 288. Divide both sides by 16, and M equals 18. So this idea of similar triangles can be used to find the heights of objects and structures that cannot be directly measured. So let's say we have a flagpole. And it's too high to measure. We want to know how high it is. So we can use shadows and some math to find the length of that flagpole. All right, we were given the length of a shadow of a flagpole is 20 feet. All right, here's the flagpole, here's the shadow, 20-foot shadow. Over here, we got a yardstick. Now we know yardstick is 3 feet, so this is 3 feet high and casts a shadow of a half of a foot. So we're going to use the corresponding sides of these two triangles to create a proportion. And a lot of different ways you can do it. You can do h over 3 equals 20 over 0.5, consistent like that. Or you can do h over 20 equals 3 over 0.5. As long as you're consistent in how you set these up. All right, so I'm going to do h over 20. All right. Vertical over horizontal, and then vertical over horizontal. Now we have a portion, we can set this thing up, 0.5 times h. And 20 times 3, so 0.5h equals 60. Divide those sides by 0.5 and you get 120. The flagpole is 120 feet high. So that is a gigantic flagpole. Now sometimes the similar triangles are going to overlap each other. And in this case, it's really helpful to just draw them separately. All right, so we have here a light source up here at T. It's a street light. And we also have some guy here who is 6 feet tall. He is 8 feet from the light. And his shadow is 4 feet. And we want to know how tall is the street light. All right, well, we have two triangles here. We've got the smaller triangle, and then we have the bigger triangle. So I'm just going to draw the bigger triangle separately so I don't have the little one there confusing things. All right, so let's figure out the length here. We have 8 here and 4 here. The total length is, add them together, 12. All right, now we're just going to look at this triangle here. We can just kind of ignore this. Compare this triangle with this triangle. All right, so I'm going to create a proportion here. Vertical over horizontal for the large triangle, h over 12 equals vertical over horizontal, 6 over 4. All right, now let's solve this proportion. H times 4, that's 4h equals 12 times 6. Solve that proportion, we get a light that is 18 feet high. All right, next up, got a boat. It's come untied and is floated away on the lake. And we're right next to a cliff. So here's the cliff. Here's the lake. And here is the boat. So she's standing on the cliff is 35 feet above the water. Okay, she's up here. So this is 35 feet here. She's 10 feet away from the edge of a cliff. And she is 5.5 feet tall. Now by connecting a line of sight there, we've created two similar triangles. And we're going to find out how far is this boat away from the cliff. Alright, so I'm just going to set up the same way I did last time. Vertical over horizontal for the small triangle. So that's 5.5 over 10. And then vertical over horizontal for the large triangle. 35 over D. Now we'll cross multiply. 5.5 times D is 10 times 35. So that's 5.5D is 350. Divide both sides by 5.5 and we get D equals 63.6. So the boat is 63.6 feet away from the cliff. Now, last one demonstrates one way of applying a technique that's been used by explorers and people in the military for quite some time, thousands of years. Sometimes it's very helpful to be able to determine the width of a river before trying to cross it. Well, in Copper Center, Alaska, a boulder that is 7 feet high casts a shadow that is 11 feet long. All right, so you got this boulder here, and it's 7 feet high. And cast a shadow that's 11 feet long. Now we also know that there's a tree that is 22 feet tall. And the shadow is exactly the same width as the river. All right, so here's the river, here's the shadow. Now we're going to find the width of the river. All right, vertical over horizontal here, we get 7 over 11 equals vertical over horizontal here, 22 over W. Cross multiplying, 7W equals 11 times 22. So 7W is 242. And that gives us 34.6. So the river is 34.6 feet wide. And that is it for today.